We're going to look at Coulomb's law applied to now 3 charges instead of 2. And all we're really doing is looking at net force when it's when it's asking for the amount of force. And the main thing that you need to look at is the positives or negatives. So what kind of charge do you have, and therefore what way are the forces pointing? So we'll start with this example, which is in your packet. It says find the force on the leftmost particle. I'm going to start by just labeling these 1, 2, and 3. So I'll call 1, 2, 3. It doesn't matter what charge you call what force. It's arbitrary at that point. And let's list what we know. So our given information, and this is all coming from the picture. Q1 is negative 30 times 10 to the negative third coulombs. Q2 is negative 16 times 10 to the negative third coulombs. And Q3 is a positive 16 times 10 to the negative third coulombs. It also tells us the separation of the charges, and I'm sorry this got a little bit cut off, but these should be 2s. So this is 2 and this is a 2. I'm going to call this R12. This is R23. So this is just the distance between 1 and 2, the distance between 2 and 3, and then this would be R13. And I know it's confusing with the subscripts, but there is a lot of information here. So R12, the distance between charge 1 and charge 2, is 0.12 meters. R23 is also 0.12 meters. And R13, we're adding them together. So 0.12 plus 0.12 is 0.24 meters. And given all of that, we are looking for the total electric force. So this is the net electric force on the leftmost particle. So that's 1. I called that 1. If you number them differently, that's fine. So that we're not getting confused, let's look at directions. If we're looking at the forces on 1 and 2 are both negative. So the electric force between 1 and 2 will be pointing to the left because 2 is repelling 1. And then the force between 1 and 3, negative is attracted to positive, and it's also farther away. So this is going to be shorter, and this will be F electric 1, 3. This is shorter because 1 and 3 are farther apart than 1 and 2. The closer together the charges, the larger the force, the farther, the smaller it is. So I do want to show that with my arrows. This is your force diagram in a sense. So my total electric force on 1 is going to equal the electric force between 1 and 2 plus the electric force between 1 and 3. So let's start by looking at, it doesn't matter what one we start with, the electric force for 1 and 2. This equals K Q1 Q2 over R12 squared. This equals K. Our Q1 is negative 30. And actually, we just need the magnitude of the charges. So let's not get confused with the negatives. The negative comes in at the end. So we'll say this is K. 30 times 10 to the negative third coulombs times 16 times 10 to the negative third coulombs over 0.12 meters squared. And that equals, and this is the electric force again between 1 and 2, that's going to equal 3 times 10 to the 8th newtons. On the picture, this force is pointing to the left, so this is going to be negative. And again, it's negative from our diagram showing that force pointing to the left. So that was the FE12. Now looking at the electric force between 1 and 3, this is K Q1 Q3 over R13 squared. So this equals K 30 times 10 to the negative third coulombs times 16 times 10 to the negative third coulombs over 0.24 meters squared. And this comes out to 7.5 times 10 to the 7th newtons. That force pointed to the right and it was smaller, so this will be positive. And our total electric force on 1 equals negative 3 times 10 to the 8th newtons plus 7.5 times 10 to the 7th newtons. And this comes out to negative 2.25 times 10 to the 8th newtons. If we look at this force diagram, my left force is greater, so that means that this should be negative since my negative 1 is greater. It's 1 sig fig, so the total net force on 1 is approximately negative 2 times 10 to the 8th newtons. I'll do the next example. It's very similar, and that's pretty much how you do these problems whenever you have 3 charges. So very straightforward. If you feel comfortable with this one, then don't keep watching. If you felt comfortable, then, if you did not feel comfortable, then keep watching for the next example. Okay, the next example, find the force from the center particle. I'll call these 1, 2, and 3, listing everything we know. Q1 is a positive 6.8 times 10 to the negative 4th coulombs. Q2 is a negative 1.4 times 10 to the negative 4th coulombs. And Q3 is a positive 9.6 times 10 to the negative 4th coulombs. The distance between 1 and 2 is 1.7 meters. The distance between 2 and 3 is 0.83 meters. And the distance between 1 and 3 is 2.53 meters. We are looking for the total electrical force on the particle in the middle, so the one I called 2. So Fe2 will equal the force between 1 and 2 plus the force between 2 and 3. So if I draw on, and this picture's not drawn to scale, but if I draw on this charge the direction of the forces, 2 and 3 are attracted to each other. So this would be Fe2, 3. 1 and 2 are also attracted to each other, but not as much as 2 and 3 are. And that's because they're farther apart. So now all we need to do is figure out what each force is and add them together. Next page so I have more room. So Fe12 equals K Q1 Q2 over R12 squared. K Q1, which was 6.8 times 10 to the negative 4th coulombs times 1.4, times 10 to the negative 4th coulombs over 1.7 meters squared. And this comes out to 296.47, keeps on going, newtons. Our little force diagram had the force between 1 and 2 going to the left. Force between 2 and 3 was going to the right, so this one would be negative. And then looking at the electric force between 2 and 3, this is equal to K Q2 Q3 over R23 squared. So K 1.4 times 10 to the negative 4th coulombs times 9.6 times 10 to the negative 4th coulombs all over 0.83 meters squared. This equals 1755.8, keeps on going, newtons. Just looking at the numbers, this number is larger than this number because this right force is larger than this left force, so that makes sense. Adding them together to get our total force on 2, we get negative 296.47 keeps on going newtons, plus 1755.8 keeps on going newtons. This comes out to be a positive 1459.3 newtons. 2 sig figs, so the total electrical force on 2 is approximately 1500 newtons. And this is positive because the right force was greater than the left force. That's the only thing this positive or negative means with the forces. So again, just to sum up, if you've got more than if you've got more than 2 charge, you need to look at the force from every charge acting on the charge in question, and then add them together just like you would net force. Right is positive, left is negative, and that's purely directional. Direction is determined by the sign of the charge.